This presentation is more about a particular type of installation than it's about the detailed use of SAM. The intent is to gauge the level of interest in the application of bifacial, also known as double-sided PV panels, in the hope that the simulation could eventually be incorporated into SAM. We will also further suggest that a minor modification to SAM could allow for better modeling of these panels. Okay, so let me first set the scene. In our opinion, the cost of PV panels is dropping dramatically, and we feel that the need to evaluate an installation using only one metric, that of the total annual energy output, is no longer that important. And this opens the door to explore new methods. Bifacial PV systems have an interesting advantage, especially now that rooftop installations need to consider how to load match and how to coexist with their host buildings. Okay, in my opinion, self-consumption is growing in importance as net metering fades into history and as the value of feed-in tariffs shrink and become uncertain. In Europe, for example, Italy, Spain, in fact even Germany and Austria have seen a massive erosion in the value of the feed-in tariff. Grids and buildings don't exist in isolation. Their interaction is key to a sustainable economy, and we've seen institutes like the Rocky Mountain Institute make this point, and over in Europe, the IEA Net Zero Building Task Team have expressed the same concerns. And that's really becomes very clear when you consider something called the Californian duck curve. There's a fair amount of debate as to whether this is real, whether it actually exists, but there's been a lot of rethinking of the impact of net zero buildings and their potential detrimental impact on the performance of the grid once we reach higher penetration levels. So if we start thinking about the Californian duck curve, and this data we got from the independent system operator in California, one of the biggest issues is the impact of the peak that is generated around about midday. So here you can see the actual curve. It's a double peak curve, and you can see the impact over the years as more and more PV is introduced, especially PV that generates its maximum energy during the middle of the day. So as an alternative, we suggest that perhaps the bifacial panel can be put to good use. I'll explain a little more about the bifacial panel later, but let's just assume that you understand it can generate energy with light falling on both surfaces. If you can see my cursor, not only the direct solar, but reflected solar onto both sides of the panel have these units producing energy throughout the day. And if you have a look at the blue curve over here, this is typically what you'd get from a bifacial panel that faces east-west. So it picks up the early morning sunlight earlier, and then the later energy in the evening. So in this graph, we've got the typical load curve. If I remember correctly, this is the load curve that came out of SAM. And we've then got the energy generated by an equivalent, let's call it standard panel, compared to the double peak energy from the bifacial. And we'd like to discuss that in some more detail. Quickly, first of all, we'd like to thank an American company, Prism Solar, for cooperating with us and giving us some feedback. We've spoken to a number of US-based companies producing the bifacial panels. They've all been very helpful, and some of their panels, in fact, are in the SAM database at the moment. So our concern was, were these panels being modeled correctly? We tackled that in a few ways. We first modeled two separate independent panels, looking at the energy output, and then summed it using a spreadsheet, expecting to introduce various parameters if needed. However, when we spoke to the panel manufacturers, the modeling of the bifacial system could be done, they claimed, using two subarrays and then just summing that total. So the subarrays were set up. Think of it as two virtual panels, one facing east, one facing west, and then we added that together. We understand that this doesn't model the inverter performance correctly, but there seemed to be general agreement amongst the panel
Mike, we seem to have lost your audio mid-sentence.
How long ago?
Ah, you're back. Thank you.
Yes, I noticed somebody unmuted me. Am I back now?
Okay, you're back now.
Okay, when did you lose me? Can you give me some idea?
Just about 10 seconds ago. So.
Oh, 10 seconds ago. Okay, I think that I noticed the pop-up. I was muted then. All right, so I'll just reiterate. We spoke to a number of panel manufacturers. We got feedback from them on how best to model the system. We ended up modeling the system using two subarrays, and we think of these as two virtual panels because they're really one panel. One faces east, one faces west. And according to the panel manufacturers and according to the calculations we did, the output seemed to be certainly close enough to real-world measurements. So we started thinking about how to take this a step further. Now, the energy produced by these bifacial panels can be increased dramatically if you take reflected energy from rooftops and other systems into account. We looked at adjusting the beam shading losses, and we are wondering if it's not possible that SAM at some stage could be adapted to allow for what we call a negative shading loss. That would allow us to model the extra energy reflected from building materials like PFTE, Teflon, a Teflon roofing membrane. We believe that such materials have specular reflections and could be modeled fairly well using the beam shading loss, but using a negative shading loss instead of the positive shading loss. So that would be something to consider. We think it would be a good approximation. Now let's have a look at an idea that came out of Switzerland. What they've done is taken bifacial panels and they strung them up using cables across parking lots. This allows for the energy to fall onto both surfaces, and in most cases they would face these panels east and west. Down the bottom over here, they've actually got a balustrade that uses the panel in the same way. Further, we've had a look at what we call carports or shaded carports. You can see in this case, this was a Teflon roofing membrane that they've stretched over the carports, and we understand that the reflected energy from this sort of carport or from a concrete roof, for example, may well provide the extra energy to allow bifacials to perform as well as any other standard panels. So let's look at a real-world example. We've taken bifacial panels, modeled it using Johannesburg, South African time of use tariffs. Okay, so the two vertical yellow bars over here are the peak time of use tariff points, and the blue line is the output from the bifacial. The red line is a standard panel of equivalent size, and we worked out the energy outputs, And we were surprised to see that in January, certainly not in wintertime, but in our January, which is summer, solar hemisphere summer, in January we were getting more energy out in terms of the total day energy. And when we looked at the price, the value of the energy according to the time of use tariffs, we found that the same applied. The value from a bifacial system certainly looked impressive. This wasn't quite the same in winter. We found in winter it tended to due to the changes in the time of use tariff timing, we found that we weren't getting quite the advantage from a bifacial. But certainly this did not take into account any extra reflected energy from if we had to position these panels over a reflective surface. And where would we find reflective surfaces? So we'd like to use this example. It's an airport near Boston in the US. In the beginning, they had a very large multi-story car park. At some point, they then decided to add tilted PV panels, and of course they faced them as south as possible, as you can see over here. Now that led to a number of problems. You can see the panels, the original panels. These panels are covered with shade cloth because, as you can see, early in the morning there was a lot of glare and reflection into the control tower, and your federal aviation authorities clamped down on this. A lot of debate about the performance of these panels and the reflections. Eventually, and I must state that at no time I understand any aircraft pilots were blinded, but certainly it caused discomfort for the control tower operators. Eventually they then looked at an alternative. So here's the alternative. You can see they swung the panels around. The panels now face southeast, and that's how they've now been installed. Okay, so I think that was an expensive lesson. We had a look at the outputs, and we said, well, the before number you see here in blue was when the panels were blinding the control tower people. The after number in red is how the system is set up at the moment. But we wondered if a bifacial installation would not be economically viable. So we produced a set of numbers, and if you look at the total annual energy, you can see that there is some correlation which would allow you to investigate bifacial. It certainly does look like it might work. If you look down the bottom here, the output in June certainly shows that you'd be picking up some interesting peaks to balance what we would think is the load profile for an airport. In other words, the extra energy use early in the morning and late in the day. So here again we have the blue graph. The blue line shows the before. The red line shows the after. They've swung the panels around to face east, so they get extra energy in the morning. And then, of course, we believe that the bifacial could be a good alternative. Now, the interesting thing is we haven't taken the effect of reflected energy from the bright white concrete surfaces. If we strung these panels across this bright white concrete surface, it's quite possible we'd get a lot of extra energy out of the panels. So I think that's an interesting case study. Further, we've had a look at the use of bifacial in Nairobi and Kenya, for example. Now, Nairobi is right on the equator, so we were wondering if it could give us some advantages. There is always a fair amount of debate as to how to best place PV panels on the equator, and typically they would be installed flat, sometimes at 15 degrees in a zigzag pattern, and that would be done, of course, to try and self-clean the panels. There's a fair amount of dust in Africa around the equator, and this causes a lot of soiling. So we thought, instead of installing these panels flat, what advantages would a bifacial installation give us? We looked at the soiling factors. We also note, of course, that the early morning peak is in the cooler part of the day, so that there's more energy production there. And here you can see a couple of numbers. For the vertical bifacial, we're getting more energy out than an equivalent horizontal installation. We did take extra soiling into account. We're using a soiling of about 5 to 10% for the flat PV panels and about 2% for the vertical. So it does show that bifacial is quite an attractive proposition for the equator. Okay, so at this point, I'm now going to hand back to the NREL folk, and maybe we can take a few questions.
Thank you very much, Mike. I'm now going to hand it over to Janine Freeman, who's going to handle questions.
All right, and remember that you can continue typing questions into the chat box as you go, but we have a couple questions over here for Mike. One question is, how commonly are you seeing these bifacial installations? Are you seeing that growing, or is it still sort of more in an experimental phase?
Mike, if you're responding, we can't. There you are.
Yes, I can hear you now. Sorry, somebody muted me again, but I am here. I didn't hear that question.
Hi, Mike. The question was, how commonly are you seeing these bifacial installations? Are they growing in what you're seeing, or are they sort of more still in an experimental phase?
No, I think they're very real. They certainly are available from a number of manufacturers, many of them American. We spoke to researchers in Singapore, for example, and they believed that the cost of bifacial will come down. We understand that bifacial panels are 10 to 20% more expensive than the standard panel. However, we often see better output, especially when you take the reflected energy into account.
Great, thank you. I think that also answers another one of the questions that we got about typical costs of the bifacial panels. Are you seeing that that increased cost is typically offset by the increased performance, or do they need a little bit more of a reduction in cost or increase in performance to really balance out? Speak to that balance there.
I would expect that the price is going to come down. The manufacturers we spoke to, certainly there's Panasonic, but many American manufacturers, they all felt that they would be seeing the price come down. A bifacial panel uses two panes of glass, two lights of glass, so it does weigh more. Transport and delivery probably is more expensive. We've seen it being used in balustrades around buildings, for example, quite popular in that use. But I think one of the biggest benefits or biggest advantages is when you string these panels together and hang them from tensioned wires. I think that would reduce the mounting cost. We're looking into a number of systems whereby the panels are hung above a shade port, a carport, and we think that would reduce the cost of the mounting system, the materials. We think it would reduce it. Here in South Africa, for example, we're worried about hail, and by mounting these panels vertically, by hanging them from steel ropes, we think that would reduce the risk of hail damage.
Great, thank you. We have one last question before we switch to our next presentation. You had mentioned adding negative beam shading losses in SAM. The question here is, what is the single most important update to SAM that would improve simulations of bifacial models? If it's that, or if there's also something else you might have in mind.
I think it's more about a verification process. I think some of the panels are certainly available in the database at the moment. when we spoke to the manufacturers, and I think it was Prism Solar in particular, I must thank them for the effort they put into discussing this with us. They seem to feel that there was a verification process, a validation process needed to confirm that the modeling was working correctly. And then the other issue would be, and I think this would apply not only to bifacial but to many other PV installations, is there some way that we could model the extra reflected energy from the ground? We've tried to see if the direct beam system would work, and that would require, we believe, a minor change to allow what we call the negative loss or a positive energy influence to be modeled.